Hello class, this is Mr. Hart, and in this podcast we want to start a unit on electricity. And this unit is kind of fun because we get to use electricity every single day. Most of us have phones and TVs and computers, and most people use electricity, almost every single minute of every single day, pretty much it seems like nowadays. And so we see it all the time, but not a lot of people understand how it works. Okay, so this is kind of a fun unit because we get to calculate and figure out how electricity works and why it works and how we've been able to use it in so many applications. Okay. Now before we get into it too much, let's just think about what is electricity. Okay, what do we actually mean when we say electricity? What do all these wires do? What does all this stuff and how does it all work, right? And so in physics, okay, electricity has a very specific definition. Okay, it's any movement or flow of electrons. Okay, that is what we define as electricity. And hopefully you remember from the previous science class that an electron is a negatively charged particle found in an atom. Okay, and so there's protons, neutrons, and electrons. Okay, so hopefully you remember what an electron is. Okay, but electricity is any type of movement of those electrons. However, in this class, trying to describe electricity mathematically, like when electrons are actually moving, trying to do the math for that is pretty difficult to do. So before we get into that, we're going to start with electrostatics. Okay, and electrostatics is just the study of freestanding charges, or basically standing or charges that aren't moving. Okay, so we're just going to kind of focus on, okay, the charges are sitting there, what's going to happen at that point. Okay, once we kind of get that down, then we'll start to move into electricity. Okay. But let's focus first on electrostatics. Okay, what do charges do when they're just sitting there? Okay, and again, there's going to be a lot of review from probably previous science classes, but let's recall that if you have two charges and they are the same charge, both positive or both negative, or what we call like charges, they will repel. Okay, or put a force on each other in the opposite direction. So these two charges right here would push each other away in opposite directions. Okay, like charges will repel each other. Okay, and likewise, if you have opposite charges, okay, then they will attract. Right? If you have a positive and negative charge, they will move towards each other. Okay, so you probably already knew this, but this is a very fundamental idea to a lot of the things we'll see throughout the unit. Okay, when we get to voltage and stuff like that. So kind of just keep this idea in the back of your mind. Okay, it's going to govern a lot of things regarding how electricity works. Okay. All right, so we need to be able to describe how much something repels another charge, or how much something attracts another charge, right? Kind of like with gravity, we want to be able to describe how much force there was. And so with electricity, we want to be able to describe how much force there is. But we're going to have to use slightly different quantities. Okay, and so with gravity we used mass to describe how much force there was going to be, right? It was kind of dependent on the mass. Well, in electricity, the force is going to be dependent on the amount of electric charge. Okay, and it's kind of hard to describe. It's the particle's quantity of electric buildup, you could say, or how much electric property it has. Okay, and we measure it in coulombs. Okay, it's kind of like the mass for gravity, right? How much stuff is in a material describes how much gravitational force is going to act on it. Same thing with electricity. This electric charge, how much electric stuff you have, you could say, built up in an object determines how much force it's going to be able to put out. Okay, and we'll measure those in units of coulombs, which we'll talk about in a second. Okay, and then if two things have electric charge, then they'll put an electric force on each other. Okay, and that's between any two electrically charged particles. And again, if they're like charges, they'll repel each other. If they're opposite charges, they'll attract each other. So I want you to think about something really quick. We're going to look at the calculation of how to describe the electric force in a second. It's called Coulomb's law. But before we get into it, I want you to think about how do we calculate, or what would we need to know to calculate the force between two charges. Okay, so let's say I have a positive charge here and a positive charge here. Okay, what would you need to know about these two objects to be able to describe their force of a repulsion in this case, because they're both positive? What quantities would you want to measure? Okay, So if you think about that, hopefully you realize that first thing you want to be able to describe is the charge, right? This electric charge. And you're going to need to know that for both objects, right? If you have more charge, you would expect to see more force, okay, between these objects. Also, if you think about it long enough, hopefully you realize that the distance is going to be another factor that's important. If these things are really close, then they're going to be able to put more force on each other. If they're really far away, they're going to be able to put less force. Okay, so the distance is another factor. Okay, and so we'll need to know the charges of each object and the distance between them to be able to describe how much force they're putting on each other. Okay, and just so you know, in all the equations, we're going to describe distance as r for radius. Okay, and in most equations, we'll use q to describe charge. Okay, so kind of a weird letter. I guess they just ran out of letters, I guess, and Coulomb was already taken for C. So charge is represented with Q, and distance is represented with R. So when we consider all that, then we get what is known as Coulomb's law, okay, named after the guy that basically discovered this, and it looks very similar to the gravitational equation if you notice, okay. But basically it says the electric force, okay, F is for force, is equal to K, which is just a constant. It's called Coulomb's constant. Okay, and we'll look at that in a second. And then it's K times, and again, Q means charge. So charge of object 1 times the charge of object 2. All over R squared, or the distance squared. Okay. But there we go. There's our equation, okay? And if you think about it, right, the larger the charges get, the more force you would expect, right? The further away they get, the less force you would expect, just like with gravity, okay? So it looks very similar to the gravitational equation, except we're working with charges now instead of masses, okay? So force equals K times Q1 times Q2 over R squared, okay? All right, so let's look at Coulomb's constant. So basically, he figured out this ratio that pretty much describes how much force is applied given a certain amount of coulombs, okay? And when you look at that number, it's actually quite large, okay? Coulomb's constant is equal to 8.988 times 10 to the 9th newtons meters squared over Coulomb squared, okay? That's a huge number. The electric force is very strong. Compare that to big G. Okay, if you think back to the gravitational equation, right? Big G, Henry Cavendish figured this out, right? And it was 6.67 times 10 to the negative 11, okay? And if you think about it, this is a heck of a lot bigger than this guy, right? 20 orders of magnitude larger than big G, okay? So electric force is way stronger than gravity, okay? It's a whole lot stronger, okay? And so the electric charge is a very strong force, and we can calculate how strong it is using Coulomb's constant. Okay. All right, let's try a practice problem. Okay, so what is the force between these two particles? Okay, and we can see that this is a 1 Coulomb charge 4 meters away from another 1 Coulomb charge. Okay, so first of all, I want you to think about, well, what direction is the force going to be? Because these are like charges, it's going to be in opposite directions, right? Or they're going to repel each other, okay? And then we can use the calculation to figure out how much force there is in newtons. So F, okay, equals K times Q1 times Q2 over R squared, okay? This is Q1, that's Q2. It doesn't matter which one's which, right? Because they can switch spots, it doesn't really matter. But let's say this is Q1, this is Q2. So we get that the force is equal to K times 1C times 1C over 4 meters squared. And by the way, just as a note, I usually wait to plug in K until the very end because it's such a big number. I want to make sure I do all the other math first before I try to put this in on the calculator. Okay. But 1C times 1C is 1. 1 over 4. Or 4 squared is 16, so we're going to get F equals K times 1 Coulomb squared over 16 meters squared. Okay, now we can plug in K. So we get the force equals 8.988 times 10 to the 9th newtons per Coulomb squared times meter squared. And then this guy right here times 1 Coulomb squared over 16 meters squared. Okay? So notice that meter squared cancels out with meter squared. Okay? So meter squared cancels out with meter squared. Coulomb squared cancels out with Coulomb squared. And we're left with newtons. So basically it's 8.988 times 10 to the 9 over 16 newtons. All right, and when you put that in on your calculator, you should get that the force equals 5.62 times 10 to the 8th newtons. Okay? So the force is 5.62 times 10 to the 8th newtons. All right, let's do one more. Just make sure you got it down. Go ahead and try this one on your own really quick. But you have two charges that are 3 meters apart. One is 2 coulombs, one is 1 coulomb. What will the force between these two particles be? Okay. So try it on your own really quick, but if you go through it, first of all, remember that these are opposite charges, so they're going to attract, right? They're going to move towards each other. Okay. And we can plug in their charges, okay, into the equation. So F equals K Q1 times Q2 over R squared. Okay, so that's going to give us K times. Now, when you plug in negative charges, make sure you keep the negative, and we'll explain why that's important in a second. But if you keep the negative, you get negative 2C times 1C over 3 meters squared. Okay. And then that's going to simplify down to K times negative 2 over 9. Okay. Now we can plug in K, so that's 8.988 times 10 to the 9th times negative 2 over 9. And again, notice I'm ignoring units for right now because we already showed that they'll cancel out, so we'll know we'll end up with newtons. Okay. But when we put that in, that is equal to negative 1.997 times 10 to the 9th newtons. Okay? And there you go. So that would be the force on the two charges. Okay? All right, I want you to notice a couple of things really quick, though. So first of all, notice that this is a negative, okay, a negative force. Now, does that mean that it's behaving in some weird way? Okay, because we never had negative forces before. Okay, it doesn't mean that at all. All it means is that these are moving towards each other. The force is towards each other. It's a force of attraction rather than a repulsion. Okay, if you ever end up with a negative, that's what it means. Also notice how big this number is right here, 10 to the 9th newtons. That's a billion newtons of force, or about 200 million pounds of force. Okay. Now, again, that means that the electric force is really strong, but that also means that most things aren't this charged. You won't see things that have 1 coulomb of charge very often. Okay, that's a really big number. That's a whole lot of charge. It'd probably kill you if you got in contact with it. Okay, you won't see these sizes of charges. Most things are in the micro coulomb range. Okay, when we talk about them. Okay, but again, it's still a very, very large force. Okay. The electric force is very, very strong, but most things don't have this much charge on them. Okay? Cool. So that's how you calculate the charges and the force between charges, and that's what's known as Coulomb's law. Okay, very fundamental equation in electricity. Okay? But I want you to think about something really quick. So why do these things behave so similarly, right? Why do they have these same properties? Why don't they behave in totally different ways? Okay? But if you think about it, right, they're both fundamental forces in physics, okay? They both have to spread out into the same space, okay? And so they're going to behave in the same way, okay, because they both depend on a quantity and the distance between the objects, right? And so gravity depends on the mass quantity, electric force depends on the electric quantity, but they're both spreading out into the same space. So they're both going to behave to the inverse square law over r squared, and they're both going to be dependent on the amount of their quantity, right? So it's kind of cool to think about. If you think about why they're the same, it kind of shows kind of the balance, you could say, in the universe, or something like that. But very cool to see these similarities and how physics behaves in similar ways, even in different parts of physics. Okay. All right, let's talk about some of the cool and fun things that come from electrostatics and electricity. Okay. So these are some electrostatic phenomenon. Okay. One is electric discharge, which you've probably felt before, which is a flow of electric charge through the air. If you've ever rubbed your socks on the carpet and then tried to touch the doorknob, okay, and it shocks you, that's electric discharge. You're letting a whole bunch of electric charge out. Then electric induction is creating an apparent charge caused by another nearby charge. Okay, so if you've ever rubbed a balloon on the wall and then stuck it to the wall, that's because of electric induction. So let's look at how that works, okay, and why that works. Okay, and so to help me with that, I'm going to pull up some simulations that show these two phenomena. Okay, they're PhET simulations. You've probably seen these before in my class. Okay, but let's look at these two separately. All right, so here's the first simulation, cleverly named John Travoltage. Okay, they got John Travolta here. And like I was saying, when you've rubbed your socks on the floor before and then you try and touch the doorknob, it shocks you, right? Or I used to have a trampoline when I was a kid, and we'd play on the trampoline all day, and then we'd touch the metal bars at the end of the trampoline, and it shocked you like crazy because you built all this charge up while you're jumping on the trampoline. Okay, but what's happening is basically when that happens, you rub against carpet or against the trampoline material, you're basically taking electrons from the carpet, okay? And so, built up quite a bit there, it looks like. So basically what's happening is you're getting extra electrons through your body, right? And those electrons, again, want to get as far away from each other because they repel, right? And you'll notice these electrons are kind of spreading out to the edges of his body because they want to get as far away as possible. So when they have a route that lets them escape, okay, like touching the doorknob, which is a nice metal conductor, they can escape through the doorknob, and so they'll jump to the doorknob to escape, which is what shocks you, okay? So you build up those electrons, they're going to try and get as far away from each other as possible. But as soon as you let a pathway open up, okay, they'll take that pathway, and that's what you feel as electric shock or electric discharge. All right, and then here's the second simulation to show electric induction, okay? So what happens is you take a balloon, right, and you rub it on the carpet or your hair or something, right, or the wall even, and you start to build electrons on that balloon, okay? So you build those electrons on the balloon. Then what happens if you go to the wall, notice that the electric charge that has built up in the balloon, okay, is now, okay, forcing these electrons in the wall to move away, okay? So the negatively charged balloon forces the negative charges in the wall to be pushed away. So what happens is we get this force of attraction here, okay, because those electrons now are farther away from each other. We get this force of attraction here from these electrons to these protons in the wall, okay, or the positive charge that's left over in the wall, okay. So you build up an electric charge, and then you put it near something that's, just a regular neutral charge, and it appears like it's charged because you've pushed the electrons away, okay. So this is induction, okay, causing these electrons to move, making the wall look like it's positively charged, so the balloon sticks to the wall because it's attracted to the wall now, okay. So that's electric induction. All right, so two very important phenomena, electric discharge and electric induction, okay. You'll start to notice these a lot more as you look for them, okay. But things that appear to, have electrons flow through the air because of this discharge, and electric induction you may see some examples of things that look to be charged because of other charges nearby, okay. A great way to demonstrate this, okay, if you want to do it on your own at home, is take a balloon, okay, and rub it against the wall so you build some charge on it, and then take water, okay, just pouring out of your faucet or your kitchen sink or whatever, and just put the balloon near the water, and then what you'll see is that the water will start to bend towards the balloon because of electric induction, Okay, so it's pretty cool if you can demonstrate it. So I recommend trying it out. Okay, it's really fun. All right, but one of the most famous demonstrations of electric discharge is the Van de Graaff generator. Okay, so you've probably seen these at science demo shows and things like that. This huge machine that makes your hair stand up on end. Okay, but if you think about it, all it's doing is building up a charge. Okay. So why does this little girl's hair stand up so high? Well, it's because she's got electrons all over in her hair, right? Those electrons want to be as far away as possible, right? Because they repel. So what route are they going to take? They're going to take the farthest route they can. Well, if someone has long hair, they're going to go to the very edges of their hair, okay, because it's as far away as possible as they can get. Then what happens as soon as the little girl touches something that's no longer charged? You give it a route, and then the hair falls because the electrons escape, okay, because they're no longer in her body, right? They're no longer pushing her hair out, okay? But a Van de Graaff generator works a very simple way. All it is basically rubbing your socks on the floor really fast, okay? It just has this rubber belt, basically, or I don't know if it's rubber, but it just basically pulls charges from this comb at the bottom and rubs against the comb as fast as it can, builds up charge on the outside of the Van de Graaff generator, and then it puts it on this metal rod. And so if you take the rod near the generator, it makes this electric spark from the electric discharge. Okay, but basically it's just doing the same thing that you would be doing if you rubbed your socks on the floor. It's just going really fast to build up a whole lot of charge. All right, let's cover two more concepts and then we'll call it good. Okay, the last two things we want to cover are electrical conductors and electrical insulators, which you probably have seen both of these. Okay. But electrical conductor is a material that lets electrons flow freely, whereas an electrical insulator is a material that does not let electrons flow, okay? Or at least not freely. It's very difficult to get electrons to pass through them, okay? And so you've probably seen examples of both of these. You probably know off the top of your head that metal, for example, is a great electrical conductor, whereas wood is a great electrical insulator, right? If you don't want to shock yourself, you grab something that's wooden or plastic or rubber, right? You want to insulate yourself from the material, or you want to insulate yourself from the electric charge. Okay, so some examples of conductors. Metal obviously is a great conductor. Tap water is a great conductor of electricity. Okay, which is why they tell you not to be out in the pool during a lightning storm. Okay, wood is a great insulator. You won't get much charge passing through wood. Plastic is a great insulator in most cases, and so they design a lot of things based on this idea of you don't want electricity to pass through certain objects, or you do want electricity to flow through certain objects. Okay? Alrighty, so I know that's a lot to cover, but just kind of gives us a background and a basis for talking about electricity and some other phenomenon that we'll look at in the next couple of days. Okay? But go ahead and get started on the homework. Let me know if you have any questions, and thank you for watching.